All right, today we're starting free energy and thermodynamics. And there's going to be just a lot of concepts up front, not a lot of math, which is a change from what we've been doing for a while now, which has all been math. So the whole thing with thermodynamics is kind of this idea of nature's heat tax. You can't win. Energy transactions, actually, energy transactions are like gambling in the sense of like a typical casino where you literally cannot win. Like the odds are set before you even start. So you're gonna lose in the long run. But with the first law of thermodynamics, energy is conserved in chemical processes. So all of that energy is conserved, meaning that when I burn gasoline, there's some amount of chemical potential energy there that gets burned. That all gets turned into thermal energy for the most part. We try to extract some of that energy as work, but only about 20% of it gets extracted. In terms of actually usable energy, so 20% of it goes towards actually moving the car forward. And I was curious, so I looked up like electric cars. Electric cars are like 80% efficient at turning the electrical energy from the battery into moving the car forward, which also just kind of highlights the energy density of gasoline. The fact that you can only get 20% of that energy out, and yet every gas-powered car can go farther on a full tank of gas than an electric car can go on a full battery, even though there's a huge energy efficiency disparity. But this applies to everything. So energy from the reaction goes towards moving the car, plus a bunch of heat, 80% of it heat. You can't win, you can't create energy that wasn't there to begin with. You can't even break even. So anytime you transfer energy, some of it gets lost as heat. That's why it's called the heat tax. It's kind of like every time you go and you buy food. Well, actually, if you buy food, depends on where you buy food and what you're buying. But if you buy something, there's a tax on everything that you buy, right? You can't win in terms of every time you spend money, you have to spend a little bit that goes into taxes that's not in the value of the thing that you bought. Same thing with transferring energy. So anywhere energy gets transferred, you lose a little bit as heat tax. So in general, the fewer transactions, the more efficient the energy use is, because for every transaction, you're losing some energy. So heating, oh yeah, heating with natural gas. If you're heating your home with natural gas versus heating your home with electricity, heating with natural gas is really efficient, because it turns out we can actually kind of use that heat tax, and it's pretty much 100% efficient at turning that natural gas into heat. But if you're heating with electricity, then somewhere else, energy is being generated. And if it's some type of fossil fuel, that gets burned, which creates heat, which makes steam, where you lose heat again, which generates the electricity, which has to then be transferred to you, transmitted. You lose heat there, and then that finally gets into the house, and then it also gets lost. Even just in generating the heat, not all of it gets generated as useful heat. That's probably the only time that you can hypothetically break even, is if you're turning it all into heat anyway, then the heat tax is already heat, and that's what you wanted. But in electricity, there's a lot more steps for an electric heater. They're overall less efficient. And some amount of that argument makes sense also for electric cars. All right, so the big the big point of thermodynamics is spontaneity. Why do certain reactions happen? Or why do certain processes happen under certain conditions? So why does iron rust? Why does water freeze below 0 degrees Celsius but melt above 0 degrees Celsius? For mechanical systems, it's easy to see how the system tends towards the lowest potential energy, in that if I lift up a heavy weight, that weight is going to want to fall downwards. If I spill water, it's going to run towards the lowest point. It's not so easy to see in chemical systems. So just like we have a mechanical potential energy, What we're going to try and define, or what we will define in this chapter, is some chemical potential that's an analogy, or that is analogous to mechanical potential energy. So what is it about these systems that goes towards lower energy? This is where we really got to separate. We talked about the speed of reactions, that was kinetics. Thermodynamics is not kinetics. Thermodynamics only cares about the beginning and the end. How things get from A to B in the middle doesn't really matter. Almost everything that we're going to do involves state functions, meaning that the beginning and the end is the only thing that matters. The path that you take to get there does not matter. So if we're thinking about, again, mechanical potential energy, your mechanical potential energy is the same if you start at the front of John Muir and you come up the front stairs, or if you go up the back stairs. You end up on the second floor either way. Even though it does take you longer to go to the back stairs and then come up those stairs, your mechanical potential energy is the same. So the way you get from A to B doesn't matter. And so we're not talking about kinetics here. Something might be spontaneous, but very, very slow. Other reactions will be spontaneous and very fast, but that's all kinetics. So we're just looking at the beginning, the end. Yeah, beginning and the end. And we'll also see how non-spontaneous processes aren't impossible. So just because it doesn't happen under normal conditions doesn't mean that you can't change the conditions to make that reaction happen. Usually requires an input of some sort of outside energy. So you might think of, a lot of the reactions that we look at and think about in, Chem 20, Chem 1, Chem 2, are the spontaneous reactions are usually exothermic. So you might think, well, maybe we can use chemical potential. We can think of enthalpy, or the amount of heat released or absorbed by a reaction, as this chemical potential, which would predict that all exothermic reactions are spontaneous, but it would predict that all endothermic reactions are not spontaneous, which isn't true. There are some endothermic reactions that are spontaneous. There are chemical cold packs that you can buy when you break them. Break the thing inside, the reactants mix, and then it gets colder. It's an endothermic process that's spontaneous. So enthalpy ain't it. So what else could we use? If we think about other spontaneous processes, it's like the melting of ice above 0 degrees, the evaporation of liquid water to gaseous water, the dissolution of sodium chloride in water. What do these have in common? Just come up with your own answer inside your head. You don't have to say it out loud. They're all becoming more disordered. Right? So as the ice cube melts, it goes from a solid to a liquid. In a solid, fixed positions, they can only vibrate. As it melts, it becomes liquid water. Now the water molecules can move around each other and spread out. When a liquid evaporates into gaseous water, liquid water, gaseous water, now that liquid can expand as that gas into the room and spread out. And even the dissolution of sodium chloride in water, if I have the salt all at the bottom, it's going to dissolve because it's concentrated at the bottom, and it can spread out into the rest of the water. So maybe this idea of disorder or entropy could be our chemical potential, right? Just like mechanical potential energy. And entropy does end up being that key. So the very informal definition is to think of it as disorder or randomness. The more random or disordered or spread out a system gets, the more entropy it has. Sometimes you think of this as chaos. The more chaos a system has, right? In terms of ice melting, when it's in that solid state, it's in a relatively crystal state, so it's fairly well organized. But as it melts, it becomes more chaotic. There's more motion of those water molecules. They can spread out. They could be in different places. Same thing for a gas. Even in a liquid, it's more organized than in a gas. So as that water leaves the liquid and becomes a gas, becomes more chaotic and more spread out. So at least one initial way might be to think of this in terms of chaos, randomness. A more formal definition, though, would be that it's the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. I feel like that's, I don't know, really wordy. Might take some digestion. Or by this Boltzmann's equation, it has Boltzmann's constant in it. You can say entropy, which is S, is equal to the Boltzmann constant, which is 1.38 times 10 to the negative 23. That's not what I want. I want to times the natural log in W, where W is that number of energetically equivalent ways to arrange the components of a system. So if we try and line this up and overlap it maybe with our thinking of like chaos, the number of ways that I can arrange all of the water molecules when it's in a solid is essentially just one way. It's that crystalline structure. They could be maybe vibrating in different ways, but when it melts and becomes a liquid, now there's a lot more ways that those water molecules can be arranged to describe essentially the same system as they can move around each other. So we'd say that W, the number of energetically equivalent ways, would increase. And we'll look at these units more later, but the units of this are joules per Kelvin. So energy per temperature. So we're not going to actually use this equation that much, but it is like a stepping off point. We're really trying to build up to a better equation that we can use to describe any chemical system. But there's kind of a lot of ground to cover. So if we imagine that we have a fixed amount of an ideal gas at a constant pressure, volume, and temperature, the state or macro state of the system is defined by the pressure, volume, and temperature of that system. The macro state. So the overall gas in the box, and actually, and perfect. I can have a gas. Oh, why did you do that? Let's just do intro to this visual. All right, so I've got a pressure, I've got some volume of the box, I've got all of these gas particles now that are flying around inside the box. And really the macro state that we're talking about is the volume, the pressure, and the temperature. The way that we get that volume, pressure, and temperature could be any number of positions for these molecules, these particles inside the box. And of course, when I pause it, then we lose sort of the velocity factor. But see that even some of these particles inside the box, although it is stuttery, some of them are moving really fast, some of them are moving really slow. There's a lot of variety in the particles and the number of what we call microstates. So if I pause this at any point, that represents one microstate. When I step it forward by one step, that's another microstate. And all of these different microstates represent the same macro state. And so for gas especially, there's a lot of different ways they can arrange these particles that as they collide off of each other, they have different amounts of energy, but the total adds up to one macro state. And so because that macro state for all of this is the same, the energy of the system is constant. And it's the energy of any given instant or any given moment, because even sometimes, right, we'll see like there will be different parts of the box that are more empty or more crowded with particles at any given time. All these different microstates. So how that energy gets distributed is anything but constant. It's continuously changing. The only constant is change. So at any instant, right, we might have one particle that has high kinetic energy, but another, it'll have low because it ran into one and it imparted that kinetic energy. So our number of microstates that all represent the same overall energy would be the exact internal energy distribution among particles at any one instant or in any one of those snapshots. And as we saw with all those particles in the box, all of our macro states, there's a bunch of different micro states that can describe the same macro state. But it's really, really hard to think of this as with that many particles, so we'll simplify it and think about it in terms of just a few gas particles. Or like in this system where we've got particles that have energies, different energy levels. In my system A, I have one energy level and I have both particles on that same energy level. So there's only one microstate. So each of those has 2 joules. The overall energy of the system is 4 joules. But it's not like switching those like left and right between the red and the blue one doesn't change the microstate. It's still both of them at 2 joules. Whereas system B has 2 energy levels, where either the red particle can be in that higher microstate or the blue one could be in the higher microstate, which is down here. So there's 2 different microstates. So system B, because there's more possible states that can describe the same macro state, has greater entropy. So think of all the possible combinations. And when we just got 2 things like this, right, there's only 2 possible combinations. That's still more entropy than only having one possible combination. More chaos. I'd say the entropy increases with the number of energetically equivalent ways to arrange the components. So the more different energy levels I have, the more entropy that system has. The more different ways that I can arrange my particles. We would also say that the energy is dispersed. When we have higher entropy, we have a higher dispersion of energy. So my energy spreads out over 2 different energy levels instead of being concentrated into the same energy level. So anything that's more highly dispersed or more randomized has more energy than if we concentrate all of that energy in the same spot. So that brings us to the second law of thermodynamics. And the second law of thermodynamics says for any spontaneous process, the entropy of the universe increases. And the universe part of this is important because we can decrease entropy locally, but we can only decrease entropy locally at the cost of increasing entropy on a universal scale. So the criteria for spontaneity is the entropy of the universe. So something is spontaneous if it increases the entropy of the universe. In entropy, so as I sort of described state functions earlier, entropy is a state function. So its value depends only on the state of the system. So either where it started at or where it ended at. It doesn't matter how you get from A to B. So usually we look at entropy as a change in entropy, your final minus initial. All right, so if we consider another system, now a little bit more complicated, we've got 4 particles instead of just 2. I have a gas that's in one flask, and there's a valve between them. In the other flask, there's nothing. It's the right flask, completely empty, nothing in there. If I open this valve in the middle, then the gas will expand into that vacuum, which means that it doesn't do any work because it's not pushing against anything. So the work is 0, the energy doesn't change, but the entropy changes. So by taking some of these particles at least and moving them over to the other flask, the entropy increases because now I've taken my particles and I've spread them out between the two flasks. So you can think about like the different microstates that are possible for my macro state being just like these two flasks, how are my particles distributed between the two flasks? I've got 4 particles. As long as the 4 particles are in the flasks, that's a macro state, or that describes the macro state. So in state 1, or state A, right, all of my particles are on the left. State B, all of the particles are on the right. And state C, I've got 2 particles on the left, 2 particles on the right. I guess I described that wrong. Those are each of the macro states. So how many different ways can I arrange the 4 particles in state A? State A meaning all of my particles are on the left. Their position in the flask doesn't matter. So there's really only one way that that can be arranged. And same for state B, but now in the other flask. But for state C, I have 2 particles in each flask. And if we number them, or label them, I should say, like A, B, C, D, A and B could be in the left flask, or A and B could be in the right flask, and C and D could be in the left flask. So that's a different microstate. I could have A and C in the left flask. I could have A and D in the left flask, and the other 2 in the right flask. So for A and B, only one microstate is possible, where all of the particles are on one side or on the other side. But state C has 6 different microstates. Where again, I'm just changing whether or not which particles are in the left flask. So 1, 2, 3, and 4, or it could be 2, 3, 1, and 4. It could be 1, 3, 2, and 4, 2, 4, 1, and 3, 1, 4, 2, and 3, 3, 4, 1, and 2. So even with just 4 particles, there are 6 times as many microstates with the particles distributed as there are with the particles all on one side of the other. And this is good news because it means that we don't have to worry about standing in a room and suddenly all of the particles move to that corner and we can't breathe for a bit. It's not going to happen. The microstate with all of the air molecules in that corner is 1. The number of microstates with the particles of gas in the room spread out everywhere is practically infinite. Because even if I move up to 20 particles for the system, we get like, that's on the next slide, 184,756 microstates. And if you had a 22.4 liter flask at STP, that'd be 1 mole. So 6.022 times 10 to the 23 gas particles. I don't know how to do the math. It's the same reason that like every time you shuffle a deck of cards, it's shuffled a different way, right? Like a single deck of cards has never been shuffled the same way twice ever, as long as it's shuffled randomly, because it's 52 factorial ways that you can shuffle a deck. And 52 factorial is more people than have ever existed. It's more time than has ever existed. It's more molecules that have ever existed. There's just like no way to comprehend that big of a number. So when we talk about 20 particles and we get 184,000, usually we're talking about way more than 20. And so the number of possible microstates that is distributed is always going to be more. So if we think about like opening that valve again and letting those particles move, my initial state was all of the particles in one flask, so I had 1 microstate. And then S final was 6 microstates. So we can calculate the entropy and see that we get an increase in entropy when I spread out those particles across 2 flasks. And again, in terms of like the energy of the system, we're spreading out the energy between the 2 flasks. So the second law of thermodynamics also helps us explain some things that aren't explained by the first law. First law of thermodynamics, energy cannot be created or destroyed. It puts no direction on which way that energy goes. The first law of thermodynamics has no restrictions against putting ice in water and having the ice get colder and the water get warmer. But we know that that doesn't happen. If you put ice into water, the ice is going to melt. It's going to absorb heat from the water. And the reason for that is because of the second law of thermodynamics. Partly because of this energy, or I should say, in one way you can think about it is in terms of how the energy is dispersed. So energy wants to spread out. Comparing the ice cubes to the water has a lot of heat. The ice cubes have very little heat. There would be more microstates if I could spread that heat into the ice cubes. Additionally, as the ice cubes melt, they go from being a solid to being a liquid, which also increases entropy. We can see that entropy as we change states also increases. So solids are going to have less entropy than a liquid has less entropy than a gas, because again, the number of ways that I can take those particles and move them around, randomize them, make them more chaotic. So we'd say, again, informally, that gas is more disorderly or more chaotic, but the formal definition would say that there are more energetically equivalent ways of arranging the gas particles in a gas than a liquid or a solid. So if we're looking at just like how the particles actually move, in a solid, the energy is limited to vibrations only. So over here, right, again, in a solid, particles are essentially fixed in place. They can vibrate in that place, but they cannot go anywhere outside of their spot. In a gas, the molecules can rotate, so they can be spinning. They can be vibrating also, and they can have translational energy where they are literally flying in straight lines until they run into something. So each molecule even has more ways that it can have its energy distributed. Some of its energy could be translational, some of it could be rotational, some of it could be vibrational, and it can be distributed randomly between those three. So there's more microstates even for every particle. So again, if we're thinking about disorder, if we're thinking about energy spreading out, the phase transition from a solid to a liquid is going to be a positive delta S. Phase transition from solid to gas is a positive delta S. The phase transition from a liquid to a gas is also going to be positive delta S. And increasing the number of moles of gas during a chemical reaction. So if we go from fewer moles, something like N2O2 to 2NO, increases the number of moles of gas during a chemical reaction. That would increase entropy. So we might expect for this reaction that it would be spontaneous, going from N2O2 to 2NO, because I get more particles of gas, which means more ways that I can distribute that energy across all of those particles. So for A, predict the sign of delta S for each process. Water gas to water liquid. Positive delta S, negative delta S. Negative. condensation, solid carbon dioxide sublimes. Positive. 2N2O goes to 2N, or 2N2 plus O, O2. Yeah, more particles. More particles, more entropy. Again, if we're thinking about microstates, if I have just 2 particles in my reactants, but I have 3 different particles in my products, that's now 3 particles that can all be sharing that energy and distributing it in different ways. Great. Making great time. Now we're gonna get like almost into math. Oh yeah, right. So change in state is also accompanied by an exchange of heat between the system and the surroundings. Right? If we want to boil, we want to melt, we want to melt an ice cube, we need to be putting heat into the ice to make it melt. So entropy is also related to the distribution of energy among the particles that compose matter. So we can take our delta S and come up with this new definition, which is delta S is equal to Q reversible. So Q in a reversible process, the heat exchange in a reversible process, and T is the temperature in Kelvin. Which kind of relates back to, we said the entropy is a measure of energy dispersal per unit temperature. I like it says, because these are, most of the slides from the textbook, publisher. Units of J/K make sense now. Doesn't that make sense now? It's perfect sense. I mean, in terms of the equation, sure, I guess. Like if we write this equation, Q would be in joules, the energy exchanged for some process, joules, sure. Temperature in Kelvin, okay. So that's the units of entropy. And we are going to relate that better to, or have that make more sense later. But as an example, when a substance melts, it absorbs energy from its surroundings. That energy becomes dispersed into the system, and the entropy of the system increases. So take that ice, I want to melt the ice, melt anything. It's got to absorb energy from its surroundings. So what we're saying here is that the amount of energy absorbed per some unit temperature is one way that we can define entropy. So if it absorbs 22 joules per Kelvin, that means that the energy, I guess one way to think of it is the energy surrounding the ice is higher than the energy inside of the ice. And so I am taking energy from the surroundings and I'm adding it to the ice, which spreads out the energy more. Another way to think of it is like if you had hot coffee in, well, especially in something less insulated, right? If you have something that's hot, it cools off. That energy gets dispersed to the surroundings. The amount of energy that gets dispersed depends on the temperature of the surroundings. So if it was 100, if it was like 100 degrees Fahrenheit in here, then the coffee would only cool down to 100 degrees Fahrenheit. And we would also all be having a bad time. So the amount of energy that gets exchanged depends on the temperature of the surroundings. But we'll also see more how this is important. So what is a reversible process, right? Up here, it's Q reversible. It's the amount of energy exchanged for a reversible process. This is not reversible in the sense that like physical changes are reversible. So if I melt something, then I can also freeze it again. A reversible process here is a process that reverses direction upon a really, really tiny change in temperature. or some property. So we're not talking about like ice on a countertop where the room's like 25 degrees Celsius. We're talking about ice at 0 degrees C. And if I make that temperature just a little bit warmer, it starts to melt. If I make it a little bit colder, then it starts to freeze again. So sort of right on the tipping point of melting and freezing, or right on the tipping point of boiling and condensing. So right at that state of reversible processes are at a state of equilibrium. And when we're talking about these reversible processes, we're also saying that they're highly idealized, meaning that they're probably not possible to achieve in real life. So let's do a little bit of a calculation. So calculate the change in entropy that occurs in the system when 10 grams of acetone, which is C3H6O, vaporizes from a liquid to a gas at its normal boiling point of 56.1 degrees Celsius. And the delta H of vaporization is 29.1 kilojoules per mole. So we want to calculate delta S. Delta S equals Q of a reversible process divided by the temperature in Kelvin. So I need the amount of heat that's being exchanged in joules, and I need the temperature that this is happening at in Kelvin. So I can find joules because I have the delta H of vaporization, and I have 10.0 grams of acetone. And so we can convert this into moles, because the delta H of vaporization is the amount of energy per mole. So 12.01 times 3 plus 1.01 times 6 plus 16, 58.09 grams per mole. So 10 divided by that equals 0.172 moles of acetone. And then 0.172 moles times, and this is in kilojoules per mole, but I want it in joules. So 29,100 joules per mole equals 5,009.468 joules. So 5,009.468 joules divided by the temperature in Kelvin, which is 329.25 Kelvin. So delta S equal to 15.2 joules per Kelvin. So meaning that at this temperature, the entropy is increasing by 15.2 joules, I guess, per Kelvin. So since it's at 329, I mean, it's 5,009 joules for this amount of acetone. Entropy is weird. So overall, the change in entropy, though, is increasing as this acetone vaporizes at its boiling point. Entropy of the system's increasing. So let's think about going the other way now, because we've been talking about like all the times where entropy increases So something melting, that increases entropy because now I've got more movement of the particles. Something evaporating increases energy because I have more particles, more freedom of movement in those particles. Even creating more gas increases entropy. So why does water freeze when the temperature is less than 0 degrees C? Because doesn't that decrease entropy? Right, so water freezing, that's negative delta S. But we know that the process is spontaneous. If you put water in a freezer, it's less than 0 degrees C, it freezes. So it's spontaneous. You don't have to do anything. Yeah, yeah, exactly. Because the second law of thermodynamics doesn't say for any spontaneous process, the entropy of the system increases. It's the entropy of the universe that increases. I should say the universe increases. So we're not just looking for an entropy change in our system, because yes, going from a solid to a liquid does increase the entropy of the system, which can increase the entropy of the universe, but it's dependent on the temperature. And really, this is this idea of dispersion of energy and why it's important to know that another way to increase entropy is just spread out energy. So the reason that your hot coffee or hot chocolate or whatever cools off, the reason your food cools off is because it's dispersing energy into the surroundings, which increases the entropy. So we have to distinguish between our system and the surroundings and look at those together to determine what is happening to the entropy of the universe. So the system would be like any chemical system or reaction that we're looking at. The surroundings are basically everything around that. And those two things together will always lead to a positive delta S. So the system of the entropy of my system can decrease. This could be negative as long as the entropy of the surroundings is more positive. And this is, again, where the dispersion of heat matters, because freezing is exothermic. So as that water is freezing, it's releasing heat into the surroundings. And that entropy, that heat then, as it spreads out, increases entropy of the surroundings. So release of energy into the surroundings increases the entropy of the surroundings. So it's kind of hard to like make a line close enough that's as tall as that one and then put it up here. Right, so the entropy of the system, the change in entropy of the system is smaller than the change in entropy of the surroundings, positive. So the overall change is that the entropy of the universe increases. And this is why it's important that entropy has this value of Kelvin temperature in it. Because the amount that the entropy of the surroundings increases depends on the temperature of the surroundings. When it's really cold, adding heat to the surroundings is a larger positive change. Adding any amount of heat to really cold surroundings increases entropy. So this is why freezing isn't spontaneous at all temperatures, because the magnitude of the change in entropy of the surroundings is due to the dispersal of energy. So if it's already really warm, then the amount of entropy increase to the surroundings from the ice or from the water freezing is going to be really small. I think we've got to, yeah. So for low temperatures, it's spontaneous because the amount of heat that I'm adding into the surroundings is significant. But at high temperatures, water freezing is non-spontaneous because the entropy that's being added to the surroundings, or the heat being added to the surroundings, increases the entropy less than the water freezing and becoming more organized decreases entropy. So there's a balance. And this is why we have like a tipping point, because as I decrease the surrounding temperature, the amount that the heat adds to the surroundings entropy increases at some point where it's reversible, is actually where this change in the S of the universe would be 0. And then as you get colder, the amount of entropy increase to the surroundings be greater and greater, the colder and colder it gets. So not only is entropy increase in disorder, but it's also this dispersion of energy, which is why eventually physicists predict that we'll have the heat death of the universe, where all of the energy is just completely evenly spread out and nothing will ever happen. They say that it's like 10 to the 100 years into the future. So really hope I'm not around for that. um, okay, I think then we'll come back to this. We're starting to get sort of into the mathier part on Friday.